Hello everyone, welcome to another module in this massive open online course on principles of MIMO, CDMA and OFDM wireless communications. And today we are going to talk about the characterization of the performance of wireless communication systems. So we talk about a performance analysis, that is how to characterize the performance analysis for communication systems, that is how to characterize the performance of a communication system. There are many metrics to characterize the performance of a communication system, but frequently one of the most convenient and one of the most informative metrics is the bit error rate of a communication system. So we are going to characterize the performance of a communication system in terms of the bit error rate, and we are going to describe what this bit error rate is shortly. So we are going to employ the following metric. So bit error rate which is often abbreviated as BER is a metric, is in fact a convenient metric which can be employed to characterize the performance of a communication system. So bit error rate is a metric which can be employed conveniently to characterize the performance of a communication system. So what is this bit error rate? Well, as you know, in a communication system we transmit information bits from the transmitter to the receiver, and these information bits can be represented as a digital stream of binary information symbols. So in a communication system one transmits information bits, such as, for instance, one transmits bits of information from the transmitter to bits of information from the transmitter to receiver. These are binary information symbols, for instance 1 0 0 1 1 1 0 1 0 0 0. This is a possible stream of information bits. This is also known as a bit stream. Right? This is also known as a bit stream which is transmitted from the transmitter to the receiver. However, all the transmitted bits are not received correctly by the receiver. Frequently there are errors during the reception of these bits. So there are bit errors. For instance, corresponding to this transmit stream, one might receive at the receiver, the transmit stream might be decoded as 1 0 0 1 1 0 0 0 0 0. So you can clearly see that this bit 1 transmitted bit has changed to a 0 at the receiver, and again this bit 1 here has changed to a 0. So there are bit errors. So bit errors occur during the transmission. Some of the bits are received in error. So these bits are in error, and bit errors occur during the communication bit errors occur during the communication during this communication process, and the bit error rate is that the average rate at which these bit errors occur during the communication process is termed as bit error rate. Bit error rate is simply the average rate of bit. So, bit error rate or BER bit error rate or BER is basically average rate. This is the average rate of bit error for a particular communication system. For instance, if 10,000 bits are transmitted between the transmitter and receiver, for instance, if 10,000 bits are transmitted and out of which 100 bits are received in error and 100 of these bits are received in error, then we say the average bit error rate equals the number of bits in error, that is 100, divided by the total number of bits transmitted. Therefore, this is equal to 1%, that is 100 divided by 10,000, which is 1%, or we say a bit error rate of 0.01. We say that out of 10,000 bits, if 100 bits are received in error, we say that the average bit error rate is the number of bits in error divided by the total number of bits transmitted. That is, in this case example, it is 100 divided by 10,000, which is a bit error rate of 1% or 0.01. So, this is the bit error rate, is number of bits in error divided by total number of bits transmitted number of bits in error divided by the total number of bits transmitted, which is in this case 1% or 0.01. And also frequently, since these bits, the transmitted bits over the channel and the received bits are random quantities, the bit error rate can also be expressed as a probability. Since these are random quantities, the transmitted bits, the bit error rate is frequently expressed as a probability. This is known as the probability of bit error. So, the bit error rate is frequently as a probability that is, it is denoted by the quantity Pe, and this quantity Pe is termed as the probability this quantity Pe is termed as the probability of bit error. This is the probability with which a received bit is going to be in error, and normally probability is between 0 and 1, but for the probability of bit error this is between 0 and 0.5, and we are going to see this shortly. The probability of bit error always lies between 0 and 0.5, that is the maximum possible bit error rate, that is the maximum possible BER is 0.5. The maximum possible BER is 0.5. Maximum possible bit error rate equals 0.5. So, bit error, the probability of bit error is the probability with which a received bit is in error, and this quantity lies between 0 and 0.5, correct. And also another important aspect to keep in mind when we analyze the performance as a communication system, that is, although we think of a communication system as transmitting a stream of information bits, these digital information bits, that is zeros and ones, are not directly transmitted over the channel, but rather these information bits are modulated prior to transmission over the channel. So, the information bits are modulated, these are modulated prior to the, these information bits are modulated prior to the transmission over the, these information bits are modulated prior to the transmission over the channel. And one such modulation format or one such digital modulation format, because we are going to talk about digital communication systems, is BPSK. And BPSK stands for, as many of you might be familiar, BPSK stands for binary BPSK stands for binary phase shift key, in which the information symbol 0 is modulated as the amplitude level square root of p, the information symbol 1 is modulated as the amplitude level minus square root of p. So, we have two voltage levels, square root of p and minus square root of p. So, there are two phases, the phase of square root of p is 0 and the phase of minus square root of p is 180 degrees. So, as you can see, there are two phases in this modulation scheme, therefore, it is known as binary phase shift keying transmission. This is a digital modulation format, and this is known as, this is basically known as the BPSK. This is known as the BPSK modulation format, and we are considering the value p, that is square root of p and minus square root of p, since we are setting the average power to p. So, therefore, the average power of this modulation format so, since you are transmitting, the amplitude is square root of p or minus square root of p, the average power is the square of the amplitude, and therefore, the average power of this transmission format is p, with BPSK modulated symbols of plus square root of p, amplitude plus square root of p and minus square root of p, and these amplitude, these modulated symbols are subsequently transmitted over the channel. And at the receiver, since you receive a continuous voltage level corresponding to the transmission of plus square root of p minus square root of p, we have to design an appropriate detector at the receiver. And one such simple detector is the following thing, looking at the symmetry in the transmitted symbols. If the received symbol is greater than 0, then if the received symbol is greater than 0, then we map it to 0, because we say it corresponds to a positive voltage level. If the received symbol is less than 0, that means it corresponds to a negative voltage level, then we map it to 1. So, our simple detector at the receiver, so the simple detector at the receiver if the received symbol is greater than or equal to 0, then we map it to the binary information symbol 0. If on the other hand received symbol is less than 0, we map it to the binary information symbol 1. That is, 0 and 1 are the binary information symbols. If received symbol is greater than or equal to 0, we map it to 0. If it is less than 0, we map it to 1. Therefore, this is also 0 can be also thought of as a threshold. The 0 is basically the threshold of this detector, and this is a threshold based detection process. This is a threshold based, this is a threshold based detector. It is a simple detector for a binary phase shift keying based digital communication system, and this is also known as a threshold based detector. That is, if the received voltage level is greater than or equal to 0, we map it to the binary information symbol 0. If it is less than 0, we map it to the binary information symbol 1. And now we have to consider the various channel models. So let us start by considering the performance of a simple digital communication system without fading. That is a simple communication system without any multipath propagation. That is a communication system with a wire line or a wire between the transmitter and the receiver. So let us start by modeling the performance of a simple wire line communication system without any fading. So let us start by modeling the performance of a wire line and to model the performance of a wireline communication system, I can consider a simple system with a transmitted symbol X. This symbol is the transmitted symbol. At the receiver, of course, there is going to be the corrupting influence of noise. So I have the addition of the noise at the receiver, and I have the received symbol which is Y. This is the output of the received symbol. So we are considering a wireline communication system, and this system can be modeled. So what we are developing is, this is the simple model for a wireline communication system. This is a simple model for a basic wireline communication system, which is X is the transmitted symbol, N is the noise at the receiver, and Y is the, this is the received symbol. Y is the received symbol, right. So we can express this system as Y equals X plus N. So this is a simple model for this communication system, where Y is the received symbol, which is equal to X, which is the transmitted symbol, plus N, which is the noise at the receiver. So this noise is, the first thing that you can see, that this noise is additive in nature. This noise is additive noise. Further, if this noise is Gaussian, is white Gaussian, if the noise process is a white Gaussian noise process, if this noise is a white Gaussian process, if this is white Gaussian, then this system is known as a additive white Gaussian noise channel. So then this system is known as an AWGN channel, which represents additive white Gaussian noise. So the noise is additive in nature. If in addition to that the noise process is white Gaussian, that is, it has a Gaussian probability density function, then this noise is known as additive white Gaussian noise, and the system model is known as an additive white Gaussian noise channel, which is abbreviated as AWGN. This is the abbreviation that is frequently employed. This is an AWGN channel. And further, we consider this noise to have a Gaussian probability density function. Remember, the Gaussian probability density function is given as the Gaussian PDF, that is the noise PDF which is f of, which I can denote by f of n is given as 1 over 2 pi sigma square root of sigma square e raised to minus n square divided by 2 sigma square, where we are assuming this noise is Gaussian with mean 0, variance sigma square. So, we are assuming noise to be have mean equals 0 and variance, that is the noise variance, equal to sigma square, or in other words it also says that the noise power is sigma square. Therefore, we are considering Gaussian noise which has a Gaussian probability density function with mean 0 and variance sigma square, that is noise power is sigma square. Therefore, the probability density function of the noise is 1 over square root of 2 pi sigma square times e raised to minus n square divided by 2 sigma square. This is the Gaussian probability density function, and to refresh your memory, we have already seen the shape of a Gaussian probability density function. It is a bell shaped curve which is given as follows. This is the mean, which in this case is 0, and the spread of this Gaussian is related to the variance, that is, it is proportional to the variance, that is sigma square. As the variance sigma square increases, the spread of the Gaussian curve increases. As variance increases, let me write that down, as variance increases, the spread of this Gaussian also increases. As the variance increases, the spread of this Gaussian increases, correct? And therefore, now we are considering such a channel which is an additive white Gaussian noise channel with the noise PDF following this Gaussian distribution, right? And now what we would like to do is we would like to consider the transmission of information symbols over this additive white Gaussian noise channel and analyze the bit error rate performance corresponding to the transmission of this BPSK modulated symbols over this additive white Gaussian noise channel. All right. So, I think this is a good point. What we have done is, so far is we have considered, we have developed a model for the transmission, a model for the modulation, that is BPSK modulation, a model for the channel, that is our additive white Gaussian channel, and in the next module we are going to analyze this communication system to develop expressions for the bit error rate performance of this communication system. Thank you very much.